Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us out into the vastness of the luminous world of the Andromeda Galaxy. In the clear autumn sky, far from the glow of city lights, a keen eye might spot a small, hazy smudge of light. This quiet patch, nestled in the constellation Andromeda, is not a cloud, nor a single star, but an entire sibling universe. It is Messier 31, the great Andromeda Galaxy, our closest spiral neighbor in the immense darkness of space. For millennia, it waited patiently, its true nature hidden, mistaken for a nebula, a whisper of cosmic gas. Only in the last century did we finally understand its true identity, an island of perhaps 1 trillion stars, floating in the void. This evening, we will travel across the great gulf that separates us, a journey of over 2.5 million light years. We will explore the stories held within that spinning disk of light. We will visit its bright, crowded core, trace the ancient light of its globular clusters, and contemplate the immense, slow dance of gravity that is pulling our two galaxies together for a destined, transformative meeting, billions of years in the future. It is a story of scale, of time, and of the profound, quiet majesty of the cosmos. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. The Andromeda Galaxy is the most distant object the human eye can see unaided. On a dark, moonless night, this neighboring galaxy appears as a small, faint smudge of light, a misty patch in the constellation for which it is named. This gentle glow is not a star nor a cloud of gas within our own Milky Way, but a separate island universe. It is a collection of perhaps 1 trillion stars, and the light that reaches our eyes tonight began its journey over 2.5 million years ago. This ancient light has traveled across the vast, cold emptiness between galaxies, carrying with it the story of a system larger than our own. To see, it is to see time itself, a faint postcard from the deep past, delivered to us across an ocean of intergalactic space. Our neighbor is known to astronomers as Messier 31, or M31. This formal name was given by the French astronomer Charles Messier in the 18th century, who was compiling a list of objects that were not comets, so that he and other comet hunters would not be fooled by them. He catalogued Andromeda as the 31st object on his list, describing it simply as a faint, nebulous glow. For centuries, its true nature remained a secret, guarded by its immense distance. It was simply a curiosity, a little cloud, as it had been called by the Persian astronomer Al-Sufi centuries earlier. This simple designation, M31, belies the majesty it holds, a quiet entry in a catalogue that in reality describes a trillion-star sibling to our own Milky Way, waiting patiently in the cosmic night. The light from Andromeda must travel for about 2.5 million years to reach us. This immense distance, roughly 2.54 million light-years, defines our relationship with the galaxy. It means that when we look at M31, we are seeing it as it was over 2.5 million years ago, a time when humanity's distant ancestors were first walking the Earth. The photons of light striking our retinas or telescope detectors began their immense voyage long before any recorded human history. This gap in time, this vast separation, is difficult to comprehend. It is a distance of over 14 million trillion miles, or 24 million trillion kilometers. This gulf of space makes Andromeda our closest major galactic neighbor, and yet it remains profoundly, unimaginably remote. A great disagreement, known as the Great Debate, defined our understanding of the universe. In 1920, astronomers Harlow Shapley and Heber Curtis argued over the scale of the cosmos. Shapley contended that the Milky Way was the entire universe, and that spiral nebulae like Andromeda were simply gas clouds within it. Curtis, however, argued that these objects were island universes, separate galaxies in their own right, existing far beyond our own. The debate centered on the true size of the Milky Way and the distance to these faint smudges. At the time, there was not enough evidence to definitively settle the argument. It was a profound philosophical and scientific question, a moment of uncertainty before the cosmos was about to be revealed as infinitely larger and more populated than anyone had dared to imagine. The mystery of Andromeda's nature was finally solved by the astronomer Edwin Hubble. In 1923, using the powerful new Hooker telescope at Mount Wilson Observatory, Hubble was able to observe individual stars within the fuzzy patch of M31. He identified a specific type of pulsating star known as a Cepheid variable. These stars have a unique and reliable property. Their brightness flickers at a rate directly related to their true intrinsic luminosity. By comparing this true brightness to how dim the star appeared from Earth, Hubble could calculate its distance. His calculations proved that the star and the nebula it lived in was located nearly 1 million light-years away, far outside the bounds of the Milky Way. With this discovery, the universe suddenly expanded, and Andromeda took its rightful place as a majestic, separate galaxy. The Andromeda Galaxy is a truly colossal structure, somewhat larger than our own. Its main visible disk of stars stretches roughly 150,000 to 200,000 light-years from one side to the other, depending on how you define its faint outer edge. If our eyes were sensitive enough to see its full extent in the night sky, it would still appear more than 6 times wider than the full moon. Beyond this bright, starry disk lies a faint stellar halo, a sparse sphere of ancient stars surrounding the galaxy that reaches several 100,000 light-years into space. Even farther out, a huge halo of thin, hot gas and dark matter extends to around 1 million light-years or more from the center. Taken together, this vast, invisible envelope gives Andromeda a gravitational reach that is hard to truly define, and within this volume, it holds sway over its own family of smaller satellite galaxies. While our Milky Way is vast, Andromeda is its more massive sibling, containing perhaps 1 trillion stars. Our own galaxy is estimated to hold between 100 and 400 billion stars, but Andromeda comfortably dwarfs this number. This immense population of suns contributes to its greater overall mass and luminosity. It is not just the number of stars, but also the vast reserves of gas and dark matter that contribute to its size. This river of 1 trillion lights creates a gravitational anchor in our local cluster of galaxies, a dominant force that shapes the destiny of nearby systems, including our own. Each of those trillion stars is a potential sun, many with their own planets, all bound together in a single spinning city of light across the cosmic dark. Our Milky Way and Andromeda are bound together by gravity and moving toward one another across the dark. The two galaxies are currently approaching at about 68 miles per second, or roughly 110 kilometers per second, fast enough to travel from the Earth to the Moon in about an hour, if they were connected by a straight road. For billions of years, gravity has been gently drawing these two massive systems closer across the 2.5 million light-year divide. This motion, confirmed by the slight blue shift of Andromeda's light and by careful measurements of its sideways drift, tells us that they are on course for a deep encounter. Most simulations suggest that they are likely to interact strongly and probably merge in the distant future, though the exact timing, and even whether they fully combine, is still being refined. Whatever the precise details, the two great spirals are engaged in a slow, majestic gravitational dance. If current best models are right, the first close encounter between the Milky Way and Andromeda will begin roughly 4 to 5 billion years from now. Though the galaxies are moving quickly, the distance they must cross is immense, so the interaction will be one of the slowest and most majestic events in the cosmos, unfolding over billions of years far in the future. Any distant descendants of ours may see a night sky transformed. Andromeda no longer a faint smudge, but a great, detailed spiral filling much of the sky as its arms begin to overlap with our own. If the galaxies do eventually merge, that final coalescence will take hundreds of millions of years more. Stars themselves are so widely separated that direct collisions will remain extremely rare, but their orbits will be reshaped and flung into new, complex paths as the two great gravitational structures intertwine. When the two galaxies finally merge, they will form a new, giant elliptical galaxy. This future galaxy has been given the temporary name Milkomeda. The beautiful, flat spiral disks of both Andromeda and the Milky Way will be destroyed in the merger. The gravitational interactions will sling stars out in all directions, scrambling their orderly orbits and creating a massive, rounded or football-shaped collection of stars. Most of the gas and dust will be used up in a final, brilliant burst of star formation, or expelled from the new system. The resulting galaxy will be a quieter, older place, a giant, reddish-yellow collection of aging stars, a tranquil monument to the two spirals that came together to create it, floating in the center of our local group. At the very heart of Andromeda, there is a complex and unusual double nucleus. For a long time, astronomers were puzzled by observations that showed two distinct bright points of light at the galaxy's center, instead of the single, dense core seen in most galaxies. One peak is the true center, which we now know harbors a supermassive black hole. The second, brighter peak is offset by just a few light years. The leading theory is that this second nucleus is the dense, leftover core of a smaller galaxy that Andromeda consumed or ate perhaps billions of years ago. This smaller galaxy's core is now trapped in a tight, decaying orbit around the central black hole, a lasting signature of Andromeda's long and violent history of galactic cannibalism. Guarding the true center of Andromeda's core is a supermassive black hole. Like our own Milky Way, Andromeda hosts one of these gravitational titans, but its black hole is significantly more massive. It is estimated to weigh in at around 140 million times the mass of our Sun, dwarfing the Milky Way's black hole, which is closer to 4 million solar masses. This immense object is the quiet engine at the heart of the galaxy. It is currently in a state of rest, feeding very little, but its gravitational influence is profound. It is this black hole, along with the dense cluster of stars around it, that forms the true nucleus, the gravitational anchor around which the second, offset nucleus of a devoured galaxy is forced to orbit. Andromeda does not travel through space alone. It is the dominant member of a family of galaxies. It is orbited by at least 35 smaller dwarf galaxies. Its own gravitational satellites, the two most prominent and well-known of these companions, are Messier 32 and Messier 110. Both M32 and M110 are small elliptical galaxies, visible in the same field of view as Andromeda, with a modest telescope. M32 is a compact, dense object, believed to be the stripped-down core of a larger galaxy that had a close encounter with Andromeda. M110 is more diffuse, a true dwarf elliptical. These companions, and the many fainter ones that surround them, are all part of Andromeda's court, slowly orbiting the Great Spiral, with many destined to one day be absorbed by it. The Andromeda Galaxy is a system of great age, dominated by older, cooler stars. While it has beautiful spiral arms laced with dust, its overall color is slightly more yellowish than the bluer tint often associated with younger, more vigorously star-forming spirals. This suggests that its most active period of star formation happened long ago. Our Milky Way is thought to be a somewhat more active stellar nursery, forming a few new stars each year. Andromeda, by contrast, is quieter, with a star formation rate that is probably only about a third to a half of our galaxy's current pace. It is a more settled, mature system. Its vast population of stars is dominated by ancient suns that have been shining for billions of years, giving the galaxy its gentle golden-hued light and its character of ancient, settled majesty. Surrounding the bright, visible disk of Andromeda is a vast, nearly invisible halo of stars and gas. The stellar halo is an immense, sparse sphere of ancient stars, thrown into wide, looping orbits by past galactic mergers, and it extends well beyond the main disk, out to a few 100,000 light-years from the center. Even more extensive is the halo of hot, diffuse gas and dark matter that envelops the galaxy. This gaseous halo may stretch for 1,000,000 light-years or more and contains a mass comparable to, or even exceeding, the mass locked up in the galaxy's stars. It acts like a giant atmosphere for Andromeda, preserving a record of the material from which it formed and providing a reservoir of fuel for its distant future, a ghostly, enormous presence in the intergalactic medium. The story of Andromeda's discovery begins long before the invention of the telescope. The first known record of this little cloud in the sky comes from the Persian astronomer Abd al-Rahman al-Sufi in the year 964. In his Book of Fixed Stars, a foundational text of medieval astronomy, he described it as a small cloud located in the constellation of Andromeda. He and other astronomers of the time would have observed it from the dark desert skies, a faint, mysterious patch of light whose true nature was completely unknown. For nearly 1,000 years, this was how it remained, a quiet, nebulous object catalogued by curious observers, waiting patiently for the tools that would finally reveal its true, staggering scale. The first telescopic observation of Andromeda was made by the German astronomer Simon Marius in 1612. Just a few years after the telescope was first pointed at the heavens, Marius turned his modest instrument toward the cloudy patch described by al-Sufi. He was the first human to see it with magnified vision, though he was still unable to resolve it into individual stars. He described it as looking like the light of a candle shining through a piece of horn. This poetic and accurate description captures the galaxy's appearance in a small telescope, a glowing, diffuse core that fades gently into the surrounding darkness. Marius had no way of knowing he was looking at a trillion-star universe, but his observation was the first step in that long journey of discovery. Like our own galaxy, Andromeda is home to a rich system of globular clusters. These are ancient, dense, spherical collections of hundreds of thousands, or even millions of stars, all bound tightly by their own gravity. They are like glittering snow globes, filled with some of the oldest stars in the universe. While the Milky Way has about 150 known globular clusters, Andromeda boasts a much larger family, with estimates of 450 to 500. These clusters orbit the galaxy, not in the flat disk, but in its vast outer halo, like ancient satellites. They are the surviving relics from the galaxy's formation, and studying their ancient light helps astronomers piece together the long, complex history of how Andromeda was built. One of Andromeda's globular clusters, known as Mile 2, is the brightest in our entire local group. Also called G1, this enormous cluster is a true giant, containing the mass of several million suns. It is so large and bright that it outshines even Omega Centauri, the most massive globular cluster in our own Milky Way. In fact, it is so massive that some astronomers have debated whether it is a true globular cluster at all. One theory suggests that Mile 2 may not be a cluster, but the surviving, stripped-down nucleus of a dwarf galaxy that was long ago consumed by Andromeda. It remains as a dense, bright testament to that ancient cosmic meal, a glittering prize in Andromeda's collection. The spiral arms of Andromeda are traced by dark, winding lanes of cosmic dust. While we see Andromeda tilted at an angle, these dust lanes are still prominent, appearing as dark silhouettes against the bright, starry background of the galaxy's disk. These lanes are not empty regions. They are vast, cold clouds of interstellar dust and gas, the raw materials for new stars. It is within these dark, cold regions that gravity can pull matter together, eventually igniting new suns. The Spitzer Space Telescope, which sees in infrared light, was able to peer through this dust and revealed that Andromeda's structure is more complex than a simple spiral, showing intricate rings of star formation, perhaps caused by a past collision with another, smaller galaxy. In 2017, astronomers were surprised by the discovery of a massive, rotating disk of dwarf galaxies. This thin plane of co-orbiting dwarf galaxies, all spinning in the same direction, was found around Andromeda. This discovery challenges our standard models of how galaxies form. According to current theories based on cold dark matter, satellite galaxies should be captured from all directions, resulting in a chaotic, swarm-like arrangement of orbits. Instead, this vast, thin plane, which is perhaps 1 million light-years across, suggests a more organized and coherent formation process that is not yet fully understood. It is a profound mystery, a celestial alignment that whispers of hidden rules governing the cosmos, still waiting to be deciphered by the astronomers who gaze upon it. The Andromeda Galaxy hosts a phenomenon known as a tidal stream of stars. One of the most prominent is the giant stellar stream, a vast, faint river of stars wrapping around the galaxy. This stream is not a natural part of the spiral structure, but is the leftover, stretched-out remnant of a dwarf galaxy. Billions of years ago, a smaller satellite galaxy strayed too close to Andromeda. Over eons, Andromeda's powerful gravity, its tidal forces, tore the smaller galaxy apart. Its stars were pulled out like a ribbon of light, and they now orbit as a ghostly testament to that ancient act of cosmic cannibalism. This stream, and others like it, are the fossils that astronomers use to reconstruct Andromeda's long and violent history of merging with smaller systems. A surprising discovery in Andromeda was the existence of young, blue stars near its central black hole. In most galaxies, including our own, the central core is a quiet place. Dominated by ancient red stars, the extreme gravitational forces from the supermassive black hole are expected to disrupt the gas clouds needed to form new stars. Yet, at the heart of Andromeda, astronomers found a mysterious disk of hot blue stars, all appearing to be only a few 100 million years old. How they formed in such a hostile environment is a significant puzzle. It is possible they formed further out and migrated inward, or that a gas cloud was somehow able to survive and collapse under these extreme conditions. A bold blue nursery in a place of gravitational titans. In 2015, the Hubble Space Telescope captured the largest and sharpest image ever taken of the Andromeda Galaxy. This monumental image, a mosaic of many smaller exposures, created a picture with 1.5 billion pixels. It reveals a staggering 40,000 light-year-long stretch of the galaxy's disk, showing over 100 million individual stars and thousands of star clusters. To navigate this image is to fly over the vast stellar cityscape of our neighbor. One can see the clear difference between the crowded, yellowish gold central bulge and the sparser, bluer spiral arms. This image, a tiny sliver of the whole galaxy, provides an unparalleled high-definition view, allowing us to see a galaxy much like our own in exquisite, breathtaking detail. Unlike our Milky Way, Andromeda does not have a prominent central bar structure. Our own galaxy is classified as a barred spiral galaxy. This means it has a large, straight, bar-shaped structure of stars and gas that cuts through its central core, from which the spiral arms then emerge. For a long time, it was thought that Andromeda was a simple, unbarred spiral. However, more recent and detailed observations, particularly in infrared light, which can see through the dust, have revealed that Andromeda may have a more complex structure. It appears to have a large, ring-like feature, and perhaps a small, less defined bar, or even a pseudo-bulge, suggesting its classification is more complicated, a unique blend of galactic structures that sets it apart from its Milky Way sibling. Andromeda may host one of the first strong candidates for a planet in another galaxy. In 2009, astronomers studying a brief microlensing event in M31 found evidence that it could be caused by a star in Andromeda, with a companion roughly 6 times the mass of Jupiter. In this technique, the gravity of the foreground star, and any planets it might have, acts like a lens, briefly magnifying the light of a more distant background star in a very specific, telltale way. The data from this event fit the pattern expected for a star-planet system. The signal is difficult to confirm and remains only a candidate, not a firmly established detection, but it was a pioneering hint. For the first time, we had a plausible glimpse of a world that might orbit a star in an entirely different galaxy. The constellation of Andromeda, where the galaxy resides, is tied to ancient Greek mythology. The constellation itself is named for the Princess Andromeda, the daughter of King Cepheus and Queen Cassiopeia, according to the myth. Cassiopeia boasted that her daughter was more beautiful than the sea nymphs, the Nereids. This angered the god Poseidon, who sent a sea monster, Cetus, to ravage the kingdom. To save his people, Cepheus was told to sacrifice Andromeda to the monster. She was chained to a rock by the sea, but was saved at the last moment by the hero, Perseus. The gods then placed Andromeda in the stars as a constellation, where she remains, forever neighboring her parents and her rescuer, and holding the faint, misty light of the galaxy that now bears her name. Andromeda's light is approaching us with a blue shift, which is rare for a galaxy. Most galaxies in the universe are moving away from us, This is because the fabric of space itself has been expanding ever since the Big Bang, stretching the light from distant objects and shifting it towards the red end of the spectrum, an effect known as redshift Andromeda. However, is so close to us that its motion is dominated by the local pull of gravity rather than the universe's expansion. Its light is not stretched but compressed, shifting it toward the blue end of the spectrum. This blue shift is the definitive evidence, the cosmic speedometer, that confirms it is not moving away, but is instead on a direct path toward us, drawn in by our mutual gravitational embrace. The space between the Milky Way and Andromeda is not completely empty. While the 2.5 million light-year gulf is mostly a vacuum, it is also populated by the vast, extended halos of both galaxies. These are immense, invisible spheres of hot, diffuse gas and sparse, ancient stars that stretch out for 1 million light-years or more from each galaxy. This means that the outer atmospheres of our two galaxies may already be touching or kissing in the vast, dark space between them. There are also streams of stars and gas, torn from dwarf galaxies, that litter this intergalactic region. This is the faint, complex foreground of the Great Merger, a tenuous bridge of matter that already connects the two great spirals before their main disks even begin to meet. The most famous stellar explosion linked to Andromeda is not recent at all, but a mysterious outburst seen in 1885. Known today as S Andromedae, or SN 1885A, it was the first supernova ever recorded in any galaxy beyond our own. Though astronomers at the time did not yet realize that Andromeda was a separate galaxy. The object flared up near the galaxy's bright central bulge, becoming visible in small telescopes and briefly rivaling the brightness of the core itself. Observers called it a new star, assuming it was a nova within the Milky Way. Only decades later, once Andromeda's true distance was understood, did we realize they had watched the spectacular death of a star in another galaxy. Later famous supernovae, like SN 1987, A in the nearby Large Magellanic Cloud, would confirm that such titanic explosions happen in many galaxies. But S Andromedae was the first extragalactic example ever seen. The Andromeda Galaxy has a more tranquil and flocculent spiral arm structure. Our Milky Way is thought to have grand, well-defined spiral arms that wrap clearly around the galaxy. Andromeda's arms, by contrast, appear more broken, patchy, and less continuous. This is known as a flocculent spiral, which means woolly or fluffy. It looks as though its arms are made of many short, patchy segments, rather than long, sweeping arcs. This is likely the result of a more chaotic and disruptive past. It is possible that a past collision or close encounter with another galaxy, perhaps its companion M32, stirred up Andromeda's disk, shattering its once grand arms into the more fragmented, gentle pattern we see today. The Great Andromeda Galaxy is the central player in our local group of galaxies. The universe is not populated by isolated galaxies, but by galaxies clustered together in groups, bound by their shared gravity. Our local group is a small, relatively sparse neighborhood, about 10 million light-years across. It contains 3 large spiral galaxies, Andromeda, our own Milky Way, and the smaller Triangulum Galaxy. Besides these 3, there are over 50 smaller dwarf galaxies, most of which are satellites orbiting either Andromeda or the Milky Way. In this local family, Andromeda is the undisputed leader, the most massive and gravitationally dominant member, holding the entire group together and slowly pulling its companions, including us. toward its center of mass. Andromeda's massive halo is acting as a cosmic cannibal, actively absorbing smaller galaxies. Like many large galaxies, Andromeda grew to its immense size by consuming its neighbors. This process is far from over. Astronomers have found abundant evidence of this feasting in the form of stellar streams, those long rivers of stars torn from dwarf galaxies. They have also identified distinct clumps of stars in the halo that move together, the undigested remnants of galaxies devoured billions of years ago. Even today, its satellite galaxies, like M32 and M110, are on orbits that will likely see them absorbed in the distant future. Andromeda is a living, growing system, its gravitational reach pulling in and assimilating the smaller structures that stray too close. A giant ring of dust was discovered in Andromeda, likely from a past collision. Using the Spitzer Space Telescope, which sees the universe in heat-sensitive infrared light, astronomers found a massive, clumpy ring of dust deep within the galaxy. This ring is not part of the main spiral arms, but a separate feature. The most accepted theory is that this ring is the ripple effect from a galactic hit and run. It is believed that the small galaxy M32, one of Andromeda's companions, plunged directly through the disk of Andromeda about 210 million years ago. This high-speed collision would have sent a shockwave expanding outwards through Andromeda's gas, like the ripple from a stone dropped in a pond, compressing the dust and triggering a burst of new star formation in the ring we see today. The fate of our Sun will be quite different when the merger with Andromeda occurs. In 4.5 billion years, when the two galaxies begin to merge, our Sun will be a much older star. It will have already exhausted the hydrogen fuel in its core and will be swelling into a red giant. Its outer layers will be expanding, perhaps even engulfing the inner planets. While the galaxy around it is in chaos, the Sun will be going through its own final dramatic life stages. It is unlikely our Sun, or what remains of it, will collide with another star from Andromeda due to the vast distances between them. Instead, it will be thrown, along with the Earth's remnants, onto a new, long, looping orbit within the new, giant Milky Galaxy. It is tempting to imagine that one day, somewhere in the Andromeda Galaxy, a distant civilization might quietly receive a greeting from us. But if that conversation ever happens, it will unfold on an almost unimaginable timescale. So far, every deliberate radio message humanity has beamed into the cosmos, including projects like the 2008 A Message from Earth, sent toward the nearby exoplanet Gliese, 581c, only about 20 light-years away, has been aimed at stars within our own Milky Way, not at distant galaxies. Andromeda sits on an entirely different scale. At roughly 2.5 million light-years away, any radio signal we aimed at it today would not arrive there for 2.5 million years if some distant civilization in that galaxy were to notice it and send a reply. Their answer would take another 2.5 million years to return. It would be a conversation stretched across 5 million years of cosmic time, a single hopeful whisper cast into a vast ocean of darkness, with no real expectation of ever hearing an echo. The rate of new star birth in Andromeda is lower than in our own galaxy. The Milky Way is a busy stellar nursery, forging a few new stars every year, mostly within its vibrant spiral arms. Andromeda, by contrast, is a quieter system. Current estimates suggest its overall star formation rate is perhaps only half, or even as little as a third, of the Milky Way's most of its stars are old, red, and settled. While it still has regions of active star birth, they are less intense and widespread than in our own galaxy. This makes Andromeda a more mature or settled spiral, a system that has already lived through its most active and creative period. It now rests as a more ancient city of light, its trillion suns slowly burning through their remaining fuel. Andromeda has a much larger and more massive central bulge than the Milky Way. The central bulge of a spiral galaxy is the dense, tightly packed, spherical region of old stars at its core. In our Milky Way, this bulge is relatively modest, and we even have a distinct bar of stars passing through it. Andromeda's bulge, however, is enormous and exceptionally bright. It dominates the galaxy's center, containing a huge fraction of the galaxy's total mass. This massive bulge is populated almost entirely by old, yellowish-red stars, indicating that it formed very early in the galaxy's history and has not seen new star formation for billions of years. It is a vast, ancient heart, a dense sphere of 1 trillion suns. It was once thought that Andromeda was orbited by a mysterious object named M33. M33, also known as the Triangulum Galaxy, is the third largest member of our local group, a beautiful spiral galaxy in its own right. Because it appears relatively close to Andromeda in the sky and is much smaller, many astronomers long assumed it was a satellite galaxy, trapped in orbit around the much larger M31. However, more recent and precise measurements of M33's motion through space have challenged this. The data suggests that M33 is likely on its first pass by Andromeda and may not be gravitationally bound at all. It may be a separate, independent traveler, just passing through the neighborhood, or perhaps on a very long, looping 30 billion year orbit. There is a mysterious X-ray glow coming from the center of Andromeda. The Chandra X-ray Observatory has detected a diffuse haze of X-ray light emanating from the galaxy's central region, within a few thousand light-years of the core. The source of this high-energy glow is not perfectly understood. It is too widespread to be coming just from the central black hole, which is currently quiet. One possibility is that it comes from thousands of undiscovered X-ray binary systems, where a normal star is orbiting a neutron star or a small black hole. Another, more exotic theory is that it could be the signal of annihilating dark matter particles, a long-sought sign of the mysterious substance that holds the galaxy together. Many of Andromeda's globular clusters may be stolen from other galaxies. Andromeda's halo is a vast, ancient place, filled with these glittering, dense clusters of stars. There are hundreds of them, far more than in our own Milky Way, and astronomers have long wondered about their origin. By studying the chemical makeup and motions of these clusters, a new story has emerged. It appears a significant portion of them do not share the same chemical DNA as the main galaxy. Their compositions are different, suggesting they were not born within Andromeda, but were instead captured. They are the surviving, glittering cores of smaller dwarf galaxies that were consumed by Andromeda over billions of years. Each cluster is a trophy, a beautiful remnant of a long-past cosmic feast. These ancient, stolen jewels now orbit their captor, a testament to the galaxy's long history of growth, a quiet, sparkling record of worlds that once were. The largest Hubble Space Telescope program ever undertaken was a survey of the Andromeda Galaxy. This monumental project was given the name the Panchromatic Hubble Andromeda Treasury, or PHAT. It was a vast, ambitious effort to map a significant portion of our neighboring galaxy in unprecedented detail, Using Hubble's powerful vision, the survey captured images in wavelengths from ultraviolet to infrared, creating a composite view that revealed the galaxy's stellar-rich tapestry. The main goal was to move beyond seeing the galaxy as a single entity, and instead resolve it into its individual components. The final mosaic, stitched together from thousands of images, catalogued the brightness, color, and location of over 100 million individual stars. It transformed our view of Andromeda from a misty cloud into a true city of stars, each light a story, now readable in our cosmic library. We see the Andromeda Galaxy at a dramatic, tilted angle. When we gaze at M31, we are not seeing it face on, like a beautiful full spiral, nor are we seeing it perfectly edge on, as a thin sliver of light. Instead, it is inclined to our line of sight by about 77 degrees. This specific angle is a blessing and a challenge for astronomers. The steep tilt, just 13 degrees from being perfectly edge on, allows us to see the three-dimensional structure of its central bulge rising above the disk. It also dramatically highlights the dark, silhouetted dust lanes. However, this tilt also makes it much more difficult to trace the spiral arms and understand the galaxy's true shape. Astronomers must use complex models to de-project the galaxy's image, mathematically tilting it back to see what it would look like from above. It presents itself to us in a grand, cinematic pose, a celestial portrait that reveals its depth, but still keeps its full, flat structure a partial mystery. The first maps made of Andromeda used radio waves instead of visible light. In the 1950s, the new science of radio astronomy allowed us to see the universe in a completely different way. Instead of the gentle light of stars, radio telescopes detect the faint, long wavelength emissions from cool hydrogen gas, the fundamental building block of stars and galaxies. When radio astronomers first turned their large dishes toward M31, they were not mapping stars. They were mapping the vast, invisible clouds of neutral hydrogen gas that permeate the galaxy's disk. Their maps revealed that this gas extended far beyond the visible, starry edges of the galaxy, forming a much larger, more massive, rotating disk. They could even use the Doppler effect on these radio waves to measure the galaxy's rotation. This was the first time we saw the invisible Andromeda, the cold, vast reservoir of fuel that holds the potential for all its future stars. The Andromeda Galaxy is wrapped in vast, ordered magnetic fields. We often think of galaxies as being governed by gravity, but they are also shaped by another invisible force: magnetic fields, billions of times weaker than a refrigerator magnet, but stretching for thousands of light years, are woven through the galaxy's interstellar gas. Astronomers have mapped these fields by observing polarized radio waves coming from Andromeda. The data reveals a large-scale, ring-like magnetic structure, particularly strong in the region of the collision ring of dust and star formation. This magnetic skeleton is powerful enough to help guide the flow of gas, acting as a channel or a barrier. It may play a crucial role in slowing down the collapse of gas clouds, helping to regulate the pace of new star birth. The galaxy is not just a collection of stars, but a living, dynamic system, humming with a magnetic energy that stretches for millennia. As Andromeda approaches, it will slowly grow larger in our night sky. For our entire human history, Andromeda has been a faint, static smudge, a celestial constant. But on the grand timescale of the cosmos, it is a system in motion, and its approach will one day become visible. Right now, its visible disk is already 6 times the width of the full moon. Though its faintness hides this from us, over the next billion years, and then the next. Its apparent size will subtly increase. But the true transformation will happen in the final billion years before the merger. In roughly 3.75 billion years, Andromeda will have grown so large and bright that it will be a spectacular, detailed object in the sky, its spiral arms and bright core clearly visible. It will dominate the night, a celestial partner looming ever closer, a breathtaking sight for any eyes that are there to witness it. The stars in Andromeda's halo are ancient, but they tell a complex story of age. The stellar halo of a galaxy, that vast, sparse sphere of stars surrounding the main disk, is like its attic. It is where the oldest, most ancient relics are stored. Using the Hubble Space Telescope, scientists have been able to look at individual stars in Andromeda's halo and measure their age. They found, as expected, a population of truly ancient stars, over 12 billion years old, that were born in the first chaotic days of the universe. But they also found a surprise. There is a second, distinct population of younger stars, perhaps only 6 to 8 billion years old. This discovery proved that Andromeda's halo was not built all at once, but was formed in at least 2 distinct epochs, one very early and one much later, likely from the violent disruption of a large satellite galaxy. Andromeda is our partner in a colossal structure known as the Laniakea supercluster. Our local group, containing the Milky Way and Andromeda, is not isolated. It is a small part of a much, much larger cosmic structure. This grand collection of galaxies is called a supercluster, a web of galaxy groups and clusters all flowing together. In 2014, astronomers defined our home supercluster and named it Laniakea, a Hawaiian word meaning immeasurable heaven. This structure contains over 100,000 galaxies and stretches for more than 500 million light-years. It is not a static object, but a dynamic one, defined by the paths of the galaxies within it. Laniakea is a gravitational basin, and every galaxy inside it, including Andromeda and our own Milky Way, is flowing along the filaments of this cosmic web toward the great attractor. Andromeda is not just our neighbor, but our fellow traveler on a shared billion-year journey. The stars in Andromeda's outer edges are moving unexpectedly fast. One of the most profound discoveries in modern astronomy came from measuring the rotation of spiral galaxies, and Andromeda was a key piece of evidence. Just like a planet, stars farther from the dense center should orbit more slowly. When astronomers, such as Vera Rubin in the 1970s, measured the rotation speed of Andromeda, they found something that defied this law. The stars in the outer, faint regions of the disk were moving just as fast, if not faster, than the stars near the center. This flat rotation curve made no sense. There was not enough visible matter, stars, gas, and dust, to provide the gravitational grip needed to keep these fast-moving stars from flying off into space. Andromeda's rapid, impossible spin is held together by a vast, unseen scaffold of dark matter, a mysterious substance that outweighs all of its trillion stars. Andromeda's small companion, M32, is a mysterious and compact fossil galaxy. The Dwarf galaxy, Messier 32, is a strange object. It is small, but incredibly dense, and orbits very close to the main Andromeda spiral. It appears to be almost nothing but a naked galactic core, a bulge without a disk. This has led to the leading theory that M32 is the victim of a galactic mugging. It was likely once a much larger spiral galaxy, perhaps the very one that plunged through Andromeda's disk 210 million years ago. During that close encounter, Andromeda's powerful tidal forces would have stripped away eons all of M32's outer spiral arms and disk. All that was left behind was its dense, resilient central bulge, which we now see as the compact dwarf M32. It remains a loyal, if diminished, companion, its own grand history erased, now just a bright, dense memory orbiting the system that consumed it. In ultraviolet light, Andromeda reveals its most active and youthful regions. When we see Andromeda in visible light, we are mostly seeing the gentle yellowish glow of its trillions of older stars. But when we look with a telescope that can see high-energy ultraviolet, or UV, light, a completely different galaxy appears. This is the light produced by the most massive, hottest, and youngest stars. These stars are so energetic that they burn through their fuel in just a few million years, so they are only found in active stellar nurseries. The Galaxy Evolution Explorer satellite took a stunning UV portrait of M31. It revealed that the galaxy's spiral arms are not just dusty, but are traced by glittering, beaded strings of star formation. The most prominent feature is a bright, blue ring of star birth, about 150,000 light-years across, far out in the galaxy's suburbs. This ultraviolet view shows us the living, breathing Andromeda. The first photograph of Andromeda revealed its true spiral nature. Before photography, astronomers could only sketch what they saw through the eyepiece. The human eye is not good at collecting faint light, so Andromeda always appeared as a simple, fuzzy oval, a nebula with a bright center. In 1888, an amateur astronomer named Isaac Roberts in England attached a camera to his 20-inch or 50-centimeter telescope. He pointed it at the Andromeda Nebula and exposed the photographic plate for 4 hours. When he developed the image, the result was a revelation. For the first time, the faint, swirling dark dust lanes and the hint of a spiral structure were captured. While he still believed it was a solar system forming, his photograph was the first concrete evidence that this object was far more complex than a simple cloud. It was the first true portrait of our neighbor, a ghostly image holding a secret. The fate of the Triangulum Galaxy is tied to the Andromeda-Milky Way merger. The Triangulum Galaxy, or M33, is the third largest member of our local group. It is a beautiful spiral, but much smaller than either the Milky Way or Andromeda. It is currently a companion to Andromeda, though its orbit is very wide and uncertain. What will happen to this smaller galaxy when its two giant neighbors collide? Simulations of the Great Merger provide a few possible answers. In some models, as Andromeda and the Milky Way merge, M33 is thrown violently onto a new, long orbit, becoming a distant satellite of the new Andromeda Galaxy. In other scenarios, M33 may not be able to escape the combined gravitational pull. It may eventually, after billions more years, spiral inward and be consumed itself, its own stars added to the new giant elliptical galaxy. Andromeda's central core has a surprising hole of cold dust. We often think of galactic centers as places of great density, full of stars, gas, and dust, all swirling around the central black hole. This is largely true for our own Milky Way. Andromeda, however, is different. When astronomers use the Herschel Space Observatory to look at the galaxy in far infrared light, which traces cold dust, they found a curious void. While the galaxy has prominent dust rings and dusty spiral arms, the central few thousand light-years are surprisingly empty of this cold material. One leading theory for this clean center is the galaxy's history of mergers. A past collision could have gravitationally scoured the region, flinging the dust and gas out of the core, or triggering a burst of star formation that used it all up. Its heart is a place of ancient stars, a heart that has been swept clean. Andromeda's stellar disk is much larger than it appears, with vast, faint suburbs. The bright, photogenic part of Andromeda, the part we see in most pictures, is its central bulge and inner spiral arms. This region is dense with stars and dust, a bustling galactic city. But recent, extremely deep sky surveys have revealed that the galaxy's flat disk structure extends much, much further out than previously thought. This outer disk, or stellar suburbs, is a vast, faint, and sparsely populated region. The stars here are few and far between, but they still follow the same orderly, rotating path. This region is so faint that it is almost invisible against the blackness of space. It is a ghostly extension of the galaxy, a quiet, sprawling neighborhood that almost doubles the total diameter of Andromeda's stellar disk, pushing it out to nearly 220,000 light-years across. Andromeda has its own galactic weather system, driven by dying stars. On Earth, our weather is driven by the sun, heating the atmosphere and oceans. In a galaxy, the weather is driven by the energy of stars. This takes the form of vast, invisible winds of hot gas. As massive stars are born, their intense radiation pushes back on the surrounding gas, and when they die in powerful supernova explosions, they blast enormous bubbles of superheated gas, enriched with heavy elements, out into the galaxy. This hot gas, with temperatures of millions of degrees, expands and rises out of the galactic disk, creating a galactic fountain. It rises into the halo, where it mixes, cools over millions of years, and then, under the pull of gravity, it rains back down onto the disk, seeding a new generation of stars. This is the galaxy's long, slow breath. Even the disk of Andromeda, its spiral arms, contains surprisingly ancient stars. We typically think of a galaxy's disk as the place where new stars are born. Full of blue, youthful suns, we expect the ancient stars, the 10-billion-year-old relics, to be in the central bulge or the outer halo. The Andromeda Galaxy, however, complicates this picture. When astronomers analyze the data from the PHAT survey, which looked deep into the disk, they found a substantial population of old, metal-poor stars. These stars were not in the bulge, but were moving in the same flat, rotating plane as the younger stars. This suggests that Andromeda's disk is itself an ancient structure, one that was already in place and forming stars 10 billion years ago. It is a galaxy with a long and stable memory, its oldest and youngest children living side by side in the same spinning cosmic home. A long, thin stream of stars near Andromeda points to a recent cosmic meal. As Andromeda feasts on smaller galaxies, it leaves behind evidence in the form of stellar streams. These long, faint ribbons of stars are the stretched-out remains of the devoured galaxy. One particularly thin or cold stream, meaning its stars are very close together and moving on a similar path, has puzzled astronomers. This structure, sometimes called the Andromeda Stream, is so coherent that it must have been created very recently in cosmic terms. If it were ancient, the stars would have had time to drift further apart. The thinness of this stream suggests it is the remnant of a dwarf galaxy that was torn apart by Andromeda's gravity, perhaps only 1 or 2 billion years ago. It is a fresh, still warm fossil, a clear sign that Andromeda's history of cannibalism is ongoing. Andromeda can be considered a two-faced galaxy with two distinct sides. Because we see Andromeda at a steep tilt, we are able to compare the near side of its disk, the edge closest to us, and the far side, the edge tilted away from us. This perspective reveals a striking difference. The near side of the galaxy, in the constellation's southern part, is where the dark, intricate dust lanes are most prominent. They are silhouetted against the bright background of the galaxy's bulge, making the spiral structure on this side appear sharp and defined. The far side, however, appears much smoother, fuzzier and brighter. This is because we are looking through the galaxy's disk to see this side, and the dust lanes are not silhouetted. The starlight from that side shines through the diffuse gas, giving it a softer, more blended appearance. The merger will end with a final, violent dance of two supermassive black holes. When the Milky Way and Andromeda collide, the stars will mostly pass harmlessly by each other, but at the very center of each galaxy, a supermassive black hole waits. Our black hole weighs 4 million suns, while Andromeda's weighs over 100 million. As the two galactic cores merge, these two colossal objects will be drawn to the new center. They will begin to orbit each other, forming a binary black hole system. This dance will be slow at first, but over millions of years, they will spiral closer and closer. As they do, they will kick out any stars that pass nearby, and in the final moments, they will merge. This final cataclysmic event will release an unimaginable burst of energy, not as light, but as gravitational waves, sending powerful ripples through the fabric of space-time itself. The Andromeda Galaxy is an anemic spiral, meaning it has less gas and dust than expected. When astronomers compare M31 to other spiral galaxies of its size, it appears to be somewhat depleted of the raw materials needed to build new stars. Its star formation rate is low, and its vast disk, while full of stars, is not as rich in cold hydrogen gas as our own Milky Way. This suggests that Andromeda may have used up most of its available fuel in a more vigorous, youthful period of star formation, billions of T-years ago. Or perhaps its long history of collisions and mergers has had a scouring effect, stripping or expelling much of its gas into its vast, diffuse halo. It is a galaxy that has passed its most creative and energetic phase, and now exists in a state of quiet, beautiful, and slow decline. Its trillion stars like embers from a once roaring fire. A strange burst of gamma rays was once detected from the direction of Andromeda. In 2014, NASA's Fermi Gamma Ray Space Telescope, which maps the most energetic light in the universe, detected a mysterious signal. It was not a sudden, bright flash, like a typical gamma ray burst, but a steady, persistent glow of high-energy rays coming from the center of M31. This was a puzzle. The galaxy's central black hole is quiet, and there were not enough known sources to account for this much gamma radiation. One intriguing, though speculative theory is that this glow could be a signal of dark matter. Some models of dark matter predict that when these elusive particles meet and annihilate each other, they should produce a faint, telltale signature of gamma rays. Andromeda's core, dense with dark matter, remains a prime suspect in this hunt. The Andromeda Galaxy may have been a very different type of galaxy in its youth. Today, we see M31 as a massive, mature spiral galaxy, a dominant force in our local group, but its past is much more chaotic. Given its massive, star-rich halo, its giant central bulge, and its history of consuming other galaxies, some astronomers believe Andromeda's original form may not have been a spiral at all. One theory suggests it was once a luminous infrared galaxy, or LIRG, a special class of galaxy defined by an incredibly intense, short-lived burst of star formation, often triggered by a major merger. According to this model, the Andromeda we see today is the calm, settled aftermath of a violent, chaotic collision that happened perhaps 8 to 10 billion years ago, a fiery youth that forged its massive core. Andromeda's light was once used to measure the expansion of the universe, but in reverse. When Edwin Hubble was first formulating his law of cosmic expansion, he measured the redshifts of many distant galaxies. He found that the farther away a galaxy was, the faster it was moving away from us. This was the first evidence for the Big Bang. However, in his collection of data, there was one glaring exception: Messier 31. The Andromeda Galaxy was not redshifted, but blue-shifted. It was the odd one out, the single data point that was moving the wrong way. This local anomaly, however, did not disprove his theory. It simply proved that the universe's expansion is a large-scale phenomenon. In our own local gravitational neighborhood, the pull of gravity is stronger than the push of expansion, and Andromeda's blue shift was the first proof of this local cosmic dance. In 2012, a microquasar was discovered in Andromeda, a miniature version of a monster. A quasar is an incredibly bright, active galactic nucleus, where a supermassive black hole is feeding so furiously it outshines its entire host galaxy. A microquasar is a similar process, but on a much smaller scale. It is a binary star system, where a normal star is orbiting a stellar mass black hole, just a few times the mass of our Sun. As the black hole pulls material from its companion star, the material heats up and fires off powerful, high-speed jets of plasma. This discovery in M31 was one of the first of its kind found in another galaxy. It is a tiny, violent engine, a pocket-sized echo of the far larger and more powerful processes that can happen at the galaxy's supermassive heart. Andromeda's companion galaxy, M110, is a dusty dwarf, which is unusual. Messier 110 is one of Andromeda's two brightest satellite galaxies, classified as a dwarf elliptical. Normally, elliptical galaxies, both large and small, are considered red and dead. This means they are filled with old red stars and contain almost no gas or dust, having finished their star-forming lives long ago, 110. However, breaks this rule. When observed with infrared telescopes, astronomers were surprised to find significant complex clouds of cold dust swirling near its center. These dark patches are subtle, but they indicate that M110 is not entirely dormant. It has somehow managed to retain, or perhaps acquire, the raw materials for new stars, and indeed, a faint scattering of young blue stars has been seen near its core. It is a galaxy that is not quite as sleepy as it first appears. The full extent of Andromeda's stellar disk was only recently understood. For decades, the edge of Andromeda was thought to be around 220,000 light-years across. This was the boundary of its bright visible disk. But astronomers wondered if it went further, into a faintness that was impossible to separate from the background sky. A team of scientists embarked on a painstaking survey, counting individual stars over a huge area around the galaxy. They found that the population of stars belonging to Andromeda's disk stars moving in the same flat, rotating plane, extended far beyond this traditional edge. This faint, sparse outer disk stretches out to at least 180,000 light-years in radius, meaning the full disk is at least 360,000 light-years across. It is a ghostly, sprawling structure, a city whose suburbs are far larger than we ever knew. The merger of our two galaxies will likely trigger a final, spectacular burst of star formation. When Andromeda and the Milky Way begin to collide, the gravitational tides will not just throw stars into new orbits, they will also violently compress the vast clouds of gas and dust that live in each galaxy's spiral arms. This compression will be like a cosmic shockwave, triggering a massive galaxy-wide starburst. Billions of new stars will ignite in a short period, a final, brilliant flash of creativity for both systems. This event will use up almost all of the remaining gas reserves. After this magnificent final flourish, the new Andromeda Galaxy will have no fuel left. It will settle into its long retirement as a giant elliptical galaxy, its star-forming days over, its skies filled only with the gentle, fading light of its aging suns. The very name nebula was once synonymous with Andromeda's mystery. For centuries, any faint, fuzzy patch of light in the sky was called a nebula, from the Latin word for cloud or mist. This single category included everything from glowing gas clouds in our own galaxy, like the Orion Nebula, to distant, unresolved star clusters. Andromeda, then known as the Andromeda Nebula, was the most famous and largest of them all. It was the archetypal mystery object. The Great Debate in 1920 was, at its heart, a debate about the true nature of these nebulae. When Edwin Hubble proved Andromeda was a separate island universe, he shattered this single category forever. The word nebula was redefined, and galaxy took its rightful place in our cosmic vocabulary, all because this one misty patch of light finally gave up its secret. The tilt of Andromeda means that one side of the galaxy appears to be spinning toward us, and the other away. This is the key to measuring how a galaxy rotates. By taking a spectrum of the light from Andromeda, astronomers can separate the light into its component colors. They can then see the Doppler effect in action. The light from the side of the disk that is rotating towards Earth is compressed or blue-shifted. The light from the side that is rotating away from Earth is stretched or red-shifted. The bright central core, however, shows little to no shift, as it is moving directly across our line of sight. By measuring the amount of this shift, astronomers can create a velocity map. This map reveals the speed of rotation at every point in the galaxy, a beautiful swirling diagram of the galaxy's vast internal motion. It is possible that Andromeda has flung globular clusters toward the Milky Way. Our two galaxies are the dominant members of the local group, and their gravitational influence extends far over the eons, as they have danced and orbited each other. They have had close passes and interactions. It is possible that during a past interaction, Andromeda's powerful gravity could have captured a dwarf galaxy, or perhaps a globular cluster, and then, through a complex three-body interaction, flung it away. Some of the most distant, isolated globular clusters and dwarf galaxies orbiting our own Milky Way, like the Leo 1 dwarf galaxy, are on such strange orbits that some astronomers have proposed they are not native to our galaxy at all. They may be refugees, cast-offs from Andromeda, sent flying across the intergalactic void to be captured by our own galaxy's gravity. Andromeda's largest globular cluster, Mile 2, has a strange chemical signature. This massive cluster, so large it may be the core of a captured dwarf galaxy, has been studied in detail. Astronomers looked at the light from its brightest stars to determine their chemical composition, their metallicity. They found that Mile 2 is not a single, simple population of stars. Instead, it seems to contain multiple generations of stars, formed at different times, with different chemical enrichments. This is very unusual for a globular cluster, which is normally a single-age population. This complexity is the strongest evidence yet that Mile 2 is not a true cluster, but a remnant galactic nucleus. It is a galaxy within a galaxy, a place that was once large enough to have its own extended history of star formation before it was consumed, leaving only its dense, bright, and chemically complex heart behind. Some of Andromeda's brightest stars are not stars at all, but vast star-forming regions. When we look at photographs of Andromeda, we see its bright, stellar core and the diffuse light of its arms, but sprinkled throughout the arms are bright, clumpy knots of light. Many of these are not individual suns, but are actually OB associations. These are enormous, loose clusters of the very youngest, biggest, and brightest stars. They are regions where a giant cloud of gas has just given birth to a new generation of stars, including massive blue O-type and B-type stars. These stars are so luminous they can be seen individually from Earth, and their combined light creates a glowing H2 region, a cloud of ionized hydrogen gas that shines brightly. These are the active nurseries of Andromeda, the bright blue beacons that trace its spiral star-forming arms. The fate of our solar system is to become a citizen of the Milky Galaxy. When the merger happens in 4.5 billion years, our solar system will likely survive. The vast emptiness between the stars makes a direct stellar collision incredibly unlikely. However, our address will change dramatically. Our Sun, along with its planets, will be thrown by the powerful changing gravitational fields onto a new and very different orbit. Instead of a stable, circular path within the Milky Way's disk, we will likely be cast onto a long, looping, chaotic orbit that takes us far out into the new, giant elliptical galaxy. We may be flung tens of thousands of light years out into the vast, sparse halo before falling back in. Our solar system will become a wanderer, a traveler in a new, larger, and more disordered home, a relic of the Milky Way. A vast stream of magnesium gas has been found between Andromeda and its satellites. Using the light of distant quasars as a backlight, astronomers can probe the invisible material in Andromeda's halo as the quasar's light passes through the gas surrounding M31. The gas absorbs specific colors, leaving a chemical fingerprint. One such study found a long, vast filament of cool magnesium gas stretching for thousands of light years between Andromeda and its companion M33. This suggests that the galaxies are not isolated, but are connected by these invisible rivers of matter. This stream could be material pulled from M33 by Andromeda's gravity, or it could be pristine, intergalactic medium gas that is flowing into both galaxies, feeding them from the cosmic web. It is a sign of a living, interconnected ecosystem, a hidden, gaseous bridge linking the two systems. The night sky will look very different as Andromeda approaches. Over the next 2 billion years, Andromeda will remain a faint smudge, slowly growing. But as it gets closer, around 3.75 billion years from now, it will be a breathtaking sight. It will be a brilliant, swirling disk of light, far larger and brighter than any star or planet, permanently filling a large patch of our sky. It will be an object of impossible, majestic beauty, a neighboring universe visible in all its spiral glory. But this beauty will be a prelude to chaos as the merger begins. Our own Milky Way, our celestial home, will appear to be torn apart. The familiar constellations will be erased as stars are thrown from their paths. The night sky will become a swirling, chaotic canvas, a testament to the most profound transformation our galaxy will ever endure. Andromeda has fast-forwarded its evolution, perhaps due to a past merger. Andromeda is a more mature galaxy than our own. It has a larger, older bulge, a lower star formation rate, and a more anemic supply of gas. This has led some astronomers to propose that Andromeda is ahead of the Milky Way in its life cycle. It is the older sibling that has already settled down. The leading theory for this accelerated aging is a major merger event that occurred in its distant past, perhaps 6 to 10 billion years ago. This massive collision would have used up a huge amount of its gas in a powerful starburst, and simultaneously puffed up its disk and bulge, accelerating its journey toward becoming a large, settled system. We are seeing a galaxy that has already lived through the kind of transformative, violent event that our own Milky Way has, so far, avoided. In the far future, Milkomeda will be an isolated island universe. After the Milky Way and Andromeda merge, the new giant elliptical galaxy will dominate the local group. Over the next 100 billion years, it will likely eat the other, smaller satellite galaxies, including M33, pulling them in one by one. But a larger, more profound change will be happening. The universe itself is expanding, and this expansion is accelerating due to dark energy. This means that all the other galaxy groups and clusters beyond our local group will be moving away from us faster and faster. Eventually, they will cross a cosmic horizon, moving away so fast that their light can never reach us again. Our Milkomeda Galaxy will be left alone, an isolated, aging island in an endless, empty, dark void. The stars in Andromeda's halo are metal poor, which is a clue to their age. In astronomy, metals are any elements heavier than hydrogen and helium. These elements are only created inside stars and are released when stars die. This means the first stars in the universe had no metals at all. Each subsequent generation of stars is born from the ashes of the previous one, so it contains more metals. When astronomers look at the stars in Andromeda's distant, ancient halo, they find they are extremely metal poor. They have very few heavy elements. This is a clear chemical birth certificate, proving they are among the oldest stars in the galaxy. They are the surviving relics from a time before Andromeda was a grand spiral, a time when the universe was young, and the first pristine building blocks of galaxies were just coming together. Andromeda's central black hole may be starved of its fuel. A 140 million solar mass black hole is a gravitational monster, but the one at Andromeda's core is surprisingly quiet. It is not a bright quasar, and it is not even as active as our own Milky Way's smaller black hole. This suggests it is currently starved of material. One reason for this might be the unusual double nucleus. The second off-center cluster of stars, the remnant of a consumed galaxy, has an eccentric orbit. As it orbits, it may act like a gravitational slingshot, scattering and deflecting any gas clouds that drift too close to the center. This companion core may be unintentionally guarding the black hole, flinging away its potential food and keeping the monster in a state of forced hibernation, leaving the galactic center a place of quiet, ancient starlight. The Andromeda Galaxy is likely surrounded by billions of rogue stars. These are intergalactic wanderers, stars that are not bound to any galaxy. It is believed that during the chaotic, violent mergers in Andromeda's past, many stars were kicked out of their home galaxies. These stars were thrown by powerful gravitational slingshots onto escape trajectories, destined to drift alone in the vast, dark void between M31 and the Milky Way. The Hubble telescope has found faint evidence of a diffuse reddish glow in the local group, which may be the combined light of these exiled suns. They are the lost children of Andromeda and of other dwarf galaxies it consumed, forming a ghostly, near-invisible population, a sea of silent, lonely stars that fills the void. The vast stellar disk of Andromeda is not perfectly flat, but is warped at its edges. Like a spinning vinyl record left in the sun, the outer regions of the galaxy's disk are bent and twisted out of the main plane. This warp is a common feature in spiral galaxies, and it is a clear sign of an ongoing gravitational conversation with other objects. This bending is likely caused by the tidal pull of its satellite galaxies, such as M33 or M32, as they orbit around and through the main system. It might also be a lingering scar from a more ancient collision. This gentle, large-scale twist in its structure is a living fossil, a visible record of the gravitational nudges and tugs that the galaxy has endured and continues to endure from its cosmic neighbors. Astronomers have used radio telescopes to listen for signals of intelligent life from Andromeda. While it may sound like science fiction, the search for extraterrestrial intelligence, or SETI, has indeed pointed its large radio dishes at our neighboring galaxy. The logic is one of numbers. If Andromeda contains 1 trillion stars, and many of them are billions of years older than our Sun, it is a prime place to look for mature, advanced civilizations. The search is a profound challenge, as any signal would be incredibly faint and would have left its source 2.5 million years ago. But in 2017, a search of M31 for powerful, obvious technological beacons was conducted. No such signals were found, but the search itself was a milestone, a moment of humanity turning its ear to a neighboring universe just to listen. Andromeda and the Milky Way are gravitationally connected in a structure called the local sheet. Our local group of galaxies is not just floating in an empty void. It is part of a larger, flatter arrangement of galaxies, a sort of cosmic suburb that is about 34 million light-years across, or about 10 megaparsecs. This structure, which includes our group and other nearby galaxy groups, is called the local sheet. All the galaxies within this sheet share a similar, coherent motion as they are pulled by the gravity of the much larger Virgo cluster. This sheet is a wall, or filament, of the cosmic web, the grand foam-like structure of the universe. It means that Andromeda is not just our neighbor. We are, in a very real sense, roommates, living together in the same flat, flowing structure of the local universe. The first star to be identified in Andromeda was a pulsating Cepheid variable. When Edwin Hubble began his search in 1923, he was not looking for any star. He was looking for a very specific kind. He needed a standard candle, a star whose true brightness was known. He found it in a Cepheid variable, a star that brightens and dims with a regular, clock-like pulse. The length of this pulse is directly tied to the star's intrinsic luminosity. Hubble measured the period of this star's flicker, which told him how bright it really was. He then compared that to how dim it appeared in his telescope. The difference was staggering, and the calculation was undeniable. The star was almost 1,000,000 light-years away. This single, flickering star, which he named V1, was the key that unlocked the true scale of the cosmos. Andromeda has been weighing itself using the tiny wobbles of its companion galaxies. One of the great challenges in astronomy is weighing a galaxy. You cannot put it on a scale. The solution is to use dark matter, the unseen mass that holds it together. Astronomers can infer this mass by watching how fast things orbit the galaxy. A new, powerful method uses the tiny, precise motions of Andromeda's satellite galaxies, like M33. Using the Hubble Space Telescope over many years, astronomers can track the sideways motion of these small galaxies as they crawl across the background of distant stars. This tiny, slow wobble, when combined with their approach or recession speed, reveals the full 3D velocity. From this, astronomers can calculate the total gravitational pull of Andromeda needed to keep them in orbit. This cosmic scale measurement has confirmed that Andromeda's mass is dominated by this invisible, dark halo. The brightness of Andromeda, while faint, is technically visible to the naked eye. The galaxy has an apparent magnitude of about 3.4. This is a measure of how bright it appears from Earth, and it is well within the limit of what the human eye can detect, which is around a magnitude of 6.5 in perfect conditions. However, this brightness is not a sharp point like a star. It is spread out over a very large area, an area, in fact, 6 times wider than the full moon. This is why it is so difficult to see. Its light is diffuse, a gentle, hazy glow. To find it, one must be far from city lights. On a clear, moonless night, you must let your eyes adapt to the darkness, and then, using averted vision, you may just spot the faint, oval mist that has been waiting patiently for 2.5 million years. The dust in Andromeda's spiral arms is made of the same material as we are. The dark, silhouetted lanes that trace the galaxy's arms are not just shadows. They are vast clouds of interstellar dust. This dust is composed of tiny, complex grains of carbon, silicon, and oxygen, the heavy elements. These are the very same elements that form rocks, planets, and even people. But these elements are not primordial. They were not made in the Big Bang. They were forged in the fiery hearts of massive stars, and then ejected into the galaxy when those stars died in supernova explosions. This dust is the recycled ash of previous generations of stars. It now waits, cold and dark, to be gathered by gravity, to form new stars, new planets, and perhaps new life, in a cycle that repeats across the universe. The merger with Andromeda will not be a collision, but a merging. The word collision implies a violent, destructive crash, like 2 cars, but this is not what will happen. The scale of galaxies is defined by emptiness. The distance between individual stars is so unimaginably vast that when the 2 galaxies pass through each other, the chance of any 2 stars directly hitting is practically 0. It would be like 2 swarms of bees flying through each other, without any 2 bees ever touching. The violence is not in the impact, but in the gravity. It is a tidal gravitational event. The 2 galaxies will not be destroyed, but they will be completely rearranged, their elegant spirals torn apart, and their stars reassigned into a new, larger, and more chaotic home. It is an act of majestic, slow, and transformative creation. The light from Andromeda is a composite, the sum of 1 trillion different stories. When we look at the faint, misty glow of M31, Our eyes are collecting photons from 1 trillion different suns. Some of that light comes from young, hot blue stars, just a few million years old, living in the spiral arms. Some comes from ancient red giant stars, 10 billion years old, in the dense central bulge. Some photons are from globular clusters, and others from glowing nebulae. All of this light, from all of these different sources, all of different ages, travels for 2.5 million years, mixing and blending together. What we see is the average, the total light of a galactic civilization. It is the combined, gentle glow of 1 trillion stars, a single, pale, ancient light that tells the complete story of a galaxy. The name Andromeda has been given to more than just the galaxy. The constellation itself is one of the 88 modern constellations, a map in our sky. But the name, rooted in myth, has inspired many other uses. There is the Andromeda strain, a fictional story of a microorganism from space. There are ships, characters, and places in countless works of fiction that bear the name, all evoking a sense of the distant, the beautiful, and the mysterious. The galaxy's scientific name, Messier 31, is practical, a catalogue number, but its common name, Andromeda, carries the weight of poetry. It connects our scientific understanding of this trillion-star universe to the ancient human impulse to look up at the dark and tell stories, a name that bridges the gap between the map and the myth. In the 1940s, Andromeda was resolved into individual stars for the first time. Edwin Hubble had proved its distance using a single, flickering Cepheid, but the true stellar nature of the galaxy remained fuzzy. The problem was our own dirty atmosphere, which blurs starlight. The solution came during World War II, at the Mount Wilson Observatory near Los Angeles. The city was under a mandatory wartime blackout to protect against air raids. This blackout plunged the surrounding area into a deep, profound darkness that astronomers had not seen for decades. In this manufactured perfect night, astronomer Walter Bard used the 100-inch Hooker telescope. In the pristine dark air, he was able, for the first time, to clearly see and resolve the faint, individual red giant stars in Andromeda's central bulge. He had pierced the nebula and seen the stars within. The stellar halo of Andromeda is clumpy, a sign of its undigested meals. A galaxy's halo should, in theory, be a smooth, diffuse sphere of ancient stars, evenly spread. But when astronomers made ultra-deep maps of Andromeda's halo, they found it was anything but smooth. It is messy, lumpy, and full of structures. They found vast, coherent streams and shells and clumps of stars, all moving together. These are the unmixed, undigested remains of the many dwarf galaxies that Andromeda has swallowed over the last few billion years. Gravity has torn them into ribbons, but it has not yet had time to stir them in completely. The halo is a chaotic, lumpy fossil record, a visible, ghostly graveyard that shows us, in plain sight, the remnants of the very worlds that Andromeda has consumed. If Andromeda were brighter, it would be the most magnificent object in our sky. The galaxy's faintness is what keeps it a secret, a prize for dark sky observers, but its true size on the sky is enormous, spanning over 3 degrees, or 6 times the apparent width of our full moon. If our eyes were as sensitive as a long-exposure camera, we would see this colossal swirling disk of light dominating the autumn constellations. It would not be a smudge, it would be a presence. We would see its bright, golden core, the dark, sweeping dust lanes, and the gentle blue glow of its spiral arms every clear night, this neighboring universe would be stretched out above us, a constant, breathtaking reminder of the scale of the cosmos, a silent, majestic spiral hanging in the dark. The final merger of Andromeda and the Milky Way is not truly the end. The creation of the giant elliptical galaxy Milkomeda will mark the end of the two beautiful spirals, but this new, larger galaxy will continue to exist for trillions of years. It will float in the center of our local group, a massive, quiet, reddish-yellow sphere of aging stars. The stars within it, including our own sun, now likely a white dwarf, will continue to orbit for eons. The galaxy will slowly fade as its last red dwarfs burn out, becoming a dark, black galaxy, but the structure itself, this massive gravitational monument, will persist. It will be a quiet, enduring testament to the two great spirals that danced together and merged, a final, stable, and unimaginably ancient object in the cold, expanding darkness of the far future. Andromeda's core may be hiding more than one black hole. The central, supermassive black hole is a 140 million solar mass titan, but it is surrounded by a complex double nucleus structure, the remnant of a consumed galaxy. This has led to an intriguing possibility. What if the consumed galaxy also had a supermassive black hole at its center? If so, the core of Andromeda might not have one, but two. Of these objects, one would be the main, central black hole, and the second, smaller one, would be trapped in orbit with the second nucleus. This would create a binary supermassive black hole system, a rare and powerful configuration. Astronomers are actively searching for the telltale gravitational or light signatures that would prove this, a hunt for a second hidden monster in the heart of our neighboring universe. The story of Andromeda is, in many ways, a story of gravity's patient power. On the scale of our lives, gravity is the force that holds us to the Earth. On the scale of the cosmos, it is the grand architect. For 2.5 million years, the light from Andromeda has been traveling toward us, carrying the story of 1 trillion stars for billions of years. The combined gravity of our two galaxies has been gently tugging them toward one another across that vast, dark gulf. A pull strong enough in our local neighborhood to overcome the general expansion of the universe. The details of their future encounter, exactly when it begins, how many close passes there will be, and whether they fully merge, are still being refined by astronomers, but all of those possibilities are written by the same quiet force. Gravity shapes the paths of galaxies, slowly rearranging them over eons, guiding them toward encounters that transform and rebuild the universe on the largest scales. Andromeda is often called a mirror to our own Milky Way. Because we are inside the Milky Way, we can never see it from the outside. Our view is blocked by dust, and we are trapped in the suburbs, unable to see the whole picture. Andromeda is our control sample. It is a large, spiral galaxy, just like ours, and it is close enough to be studied in exquisite detail. By looking at Andromeda, we can learn about ourselves. When we study its central bulge, we are seeing a reflection of our own. When we map its spiral arms, we are learning about the structure that we, too, inhabit. It is our cosmic sibling, our partner in the local group. It is the only other grand design spiral that we can study from the outside in, a beautiful external laboratory that helps us understand the nature of our own hidden galactic home. We have a more detailed map of Andromeda than we do of our own galaxy. This is one of the great ironies of astronomy. We live inside the Milky Way, yet its true shape and structure are hidden from us. We are embedded in its dusty disk, and we cannot see the other side. It is like trying to map a dense forest while standing in the middle of it. Andromeda, however, presents itself to us from a perfect external vantage point. It is laid out before us, a 2.5 million light-year journey away. We can see its entire structure, from its bright core to its faint outer halo. We can map its arms, count its clusters, and trace its streams. Because of this, our map of Andromeda's stars and structures, our understanding of its grand architecture, is in many ways more complete than the map we have of our own dusty and obscured Milky Way. The Andromeda Galaxy is, in the end, a vision of our own future. It is a more massive, more mature, and more settled galaxy than the Milky Way. Its most active, chaotic days of star formation are in its past. Its bulge is larger, its gas reserves are lower, and its history is written in the clumpy remnants of the galaxies it has already consumed. Our Milky Way is on a similar path, but we are a few billion years behind. In Andromeda, we see a preview of what our own galaxy may become, even before the Great Merger. It is our older sibling in the local group, and in its inevitable gravitational approach, it is also a vision of our shared, transformative destiny. It is a quiet, trillion-star neighbor, a constant, faint light in our sky that holds the story of our past and the key to our ultimate cosmic future. And so, our journey through the luminous world of the Andromeda Galaxy comes to a gentle close. The great, misty smudge of M31 now recedes from view. It returns to its quiet watch in the northern sky, a silent, trillion-star universe holding its secrets close. We have traveled across the 2.5 million light-years of cold, dark space that separate our home from this, our grandest neighbor. We have seen the ancient light of its globular clusters, the ghostly rivers of stars left by galaxies it has consumed, and the deep, abiding mystery of its double heart. The galaxy is not just a static object, but a living, dynamic system, a mature spiral that has seen eons pass, and one that is slowly, patiently, making its way toward us. The story of Andromeda is a story of time, written on the grandest of scales. It is a mirror reflecting the possible past and the inevitable future of our own Milky Way. The great, slow dance of gravity that pulls our two galaxies together is not an end, but a transformation, a destiny written in the laws of the cosmos. As we leave these distant shores, we carry with us the sense of that immense, quiet majesty. The light from that distant island, even as you rest, continues its long journey, a constant, gentle reminder of the vast, beautiful, and sleepy universe all around us. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of Andromeda and the gentle music carry you softly into rest. Sleep well. Good night.